Okay, let's start. Right, in TUT 3 today, you have to write forces as vectors. So, given a force, let's say I tell you the force is 100 newtons, and I ask you to write that force in terms of its components. The I component, J component, and the K component. In a Cartesian vector form, like this. There's a vector. On the left-hand side, you have the vector A. Its component in the I direction, in other words, in the X direction, then in the Y direction, and in the Z direction. Now, you're going to do this with not only forces, but later also with any vector. Whether the vector is a velocity or acceleration, you can always write a vector in terms of its I, J, and K components. Okay, now let's say you have something like this, and you want to write that force as a vector. You know the magnitude, but you don't know the I, J, and K components. Now there are three methods you can use to write the force as a Cartesian vector. Last week we discussed two of them. Now the first one is when you are given the angles, alpha, beta, and gamma, with the X, Y, and Z axis. Then you can write the force like that. That is also one of the equations I have on this paper. That's this last equation down here. Now this equation says the force as a vector is the magnitude of the force. There's a difference between F with a underscore and the F like that. That's the magnitude. This is the vector. The magnitude, cos alpha, cos beta, cos gamma. The angle with the x-axis, with the y-axis, or with the z-axis. So if you know the magnitude and you know these angles, you can write the force as a vector. Actually, you only need two angles, because you also have this equation. So if I give you alpha and beta, you can find gamma. We only need two of those angles to work out the gamma. And what I also mentioned last week, if you get something like cos squared gamma is 0.25, then cos gamma is plus or minus the square root of that, which is 0.5. And that means gamma can be 60 degrees or 120. And that you've got to decide for yourself. You've got to look at the drawing and check, is gamma angle less than 90, or is it an angle larger than 90? So this is the one method. That's your basic equation, the magnitude there, and then the cos of the angles with the three axes. So you have one or two or a couple of problems today where you'll have to use this method. The second method is where you work with the triangles, and that I also discussed last week. I said you have, in some cases, a horizontal triangle and a vertical triangle. So you have something like this. Vertical triangle and a horizontal triangle. So that is 40 degrees in the horizontal and then 60 degrees up. Rather, 40 degrees and then 60 degrees in the vertical. So here's your force, and they give you these two angles. And they say, find the X, Y, and Z components of that force. Now, okay, it's better to redraw these two triangles. You can redraw that triangle and this one separately, and then you get something like this. Well, when you get used to these problems, it's later not necessary to do this anymore. But okay, that one there, the force F is over here. 60 degrees, 90 degrees down there, because this is in the horizontal and that is a vertical line. So you get this triangle, and then this triangle here 40 degrees, then 90 over here, because this is parallel to that. So this is parallel to the y-axis, and this is the x-axis. You get a 90 degrees here. And then that line there is the base of this triangle, and is the hypotenuse of that triangle. So if you know the magnitude of this, let's say this is 100, and you know this is 100 cos 60, and then that is also 100 cos 60. And this will be this component, the z component, 100 sine 60. I think I've worked out something here, yeah. Here's the same one. And I've redrawn it here, and I've said, okay, let's make that 100 Newton. Then this will be 100 cos 60, which is 50. So that one will also be 50. That green one there. Well, it's not so clear that it's green, but that is green there. So this 50 is the same as that one over there. And then you can work out all the sides. This, of course, here will be the z component of the force. And then the x component is going to be in this direction, this one or this one. And the y component, this one or that one there. So here, the y component is then this one. And the x component is that side over there, which is this side over here. So here's your x component, y component, z component. So you can say you have an x component, and then you have a y component, and then you have a z component. Those three will give you that force F. Okay, and then it's quite easy to work out these components. Trigonometry, cos and sine, and then you just put them together, and you get here, the vector is the x component, I, plus the y component, j, plus the z component, k. What will I get if I work out the magnitude of this one over here? So I say the fx squared plus the fy squared plus the fz squared, and I take the square root of that. What will your answer be? This is mental arithmetic. That one squared plus this one squared plus that one squared, take the square root of the lot. What should you get? You should get 100, because the magnitude of this force is 100. So if you get to this point over here and you work out the magnitude of this, then you should get 100. If you don't get 100, then you made some mistake. So, okay. Right. And here's a similar problem. Also with triangles, but here your one triangle is just going down. So you have a horizontal triangle here at the top, theta degrees, and then alpha degrees down. And you have this. And once again, that angle there will be 90 because this is parallel to this. And that is the y-axis, so this is the x-axis, that's your 90 degrees. And this, of course, is 90 because this is a vertical line. And that line there is in the horizontal. So, you're going to do exactly the same. Here's your z component. This is going to be your z component, a negative z component. That one there will be the x component. And that one there will be the y component. So that one plus that one plus that one gives you this resultant. That gives you this resultant. So that's your two methods, which we also discussed last week. The one with trigonometry and the other one, and of course, if you have those angles, then you can use that equation. Okay, now the next method, which you did this week, is when you have 2 points in space. Let's say you have a point A and a point B, and there's a force of 900 between A and B. Now A and B can be any 2 points on that line. A can be over here, and B can be over there. A and B is just to give you not more or less, A and B is just to give you the direction of that force. So A and B can be anywhere over here, or B can be a little bit farther, and A to the left, or whatever. So, how do I solve this? And there's a couple of problems in today's tutorial where you have to do that. Here you use the unit vector. The force F equals its magnitude, which is 900, times the unit vector from A to B. Now, you work with different unit vectors. Before this, the I, J, and K are unit vectors. But the I is always in the X direction, and the J always in the Y direction, and the K always in the Z direction. Here you need a unit vector between A and B. So note here, from A to B, you can get a position vector. Well, let me first write it like this. The definition of the unit vector is the position vector divided by its magnitude. So, the unit vector and the position vector are in the same direction. So you have a position vector, and if you just push it together, just squeeze it together so that you get a vector of length 1. That's your unit vector. Take that whole position vector R, just squeeze it together, and you get that unit vector. Unit vector is in the same direction as the R vector. But it's only got a magnitude of 1. Every unit vector has a magnitude of 1. So this is what you have to do. You've got to work out the position vector and divide it by its magnitude. Now what's the position vector from A to B? Well, then you work with the coordinates. These coordinates. Now the vectors from A to B, now you take the coordinates of B and you subtract the coordinates of A. So your final values minus the initial value. So you take those coordinates and you subtract these coordinates. That is the vector from A to B. The final values minus the initial values. So if I do that, I'm going to get for the x coordinate minus 2 minus 2. That's minus 4. There I'm going to get 3 minus 1. That's plus 4. And the other one is 8 minus 1, which is 7. So the final values minus the initial values. You can also see it like this. Let's say you were to walk from A to B. How far will you walk in the x direction? You're at plus 2 and you're going to minus 2. So you're going to walk 4 in the negative x direction. You're starting at plus, you're stopping at minus 2. So you're going to walk 4 in the negative x direction. So here's a minus 4. In the y direction, you start at minus 1 and you go to plus 3. So you start in the negative side, on the negative side, you go to plus 3 on the positive side. So you're going to walk 4 in the positive direction. So that's why you have a plus 4. And then the same for the z coordinate. Okay, so if you're working with a position vector A, B, then it's the final coordinates minus these coordinates. If you were to work with a position vector BA, BA would be a vector from B to A. I'll get to that in a moment. So, okay, so I have that, and I divide it by the magnitude of that vector. Now, just a hint here. This magnitude here, if you work this out, you're going to get 9. Now, students quite often then they say it's minus 4 over 9, plus 4 over 9, and 7 over 9. And then they work out the decimals, and 4 divided by 9, and they get the value at 4 divided by 9, and 7 divided by 9. In this case, for example, if you get a 9 there, you can cancel the 9 into the 100, into the 900, and you get 100. It's much easier to first see what is this. If it's an integer, then you can often just cancel it in there. If it's like 3,4795, something like that, of course, then you have to work it out on your calculator. But in this case, it's going to be minus 4 over 9, and then the 900 divided by 9 will give you 100. So it's minus 400. And the same for the others. So look out for, don't just go and work out a lot of decimals. See if you can cancel out, especially when you have integers, and you can cancel it out either there or maybe over here. So that's my answer there. Okay, and once again, if I were to work out the magnitude of this vector, I'll say 400 squared plus 400 squared plus 7 squared. And I take the square root of the whole lot, then I should get 900. Are you learning? You should get 900. Okay, another question. If I take that part there without the 900, if I take that over there, and if I were to work out the magnitude of that vector, what's the magnitude of that vector? 1, because it's a unit vector. Here you have minus 4 over 9, plus 4 over 9, and 7 over 9. You work out the magnitude of that vector, square root of all the components squared, then you get 1. This magnitude is 1. Okay, but there's your vector. 400 in the negative x direction, plus 400 in the y direction, and 700 in the z direction. They often ask you, okay, you got this vector now. What's the angles, alpha, beta, and gamma, between this vector and the x, y, and z axis? Okay, and then you have the equation to do that. Cos of alpha is the x component divided by the magnitude, and the y component and the z component. So here you'll say the cos of alpha will be minus 400 divided by the magnitude. And that will give you alpha. The minus is important here. The other one is 400 over 900, that will give you beta, and the final one is 700 over 900, that will give you gamma. And of course the cos squared of alpha and the cos squared of beta and the cos squared of gamma should be 1. Cos squared of the angles is always 1. Okay, so there you have those 3 methods. Here a similar one, but the force is just working in the opposite direction. So, if I'm going to use this method with a unit vector, I'm going to say 600 times the unit vector which runs from D to C. In that direction, that's important. So you're going to take the position vector in that direction divided by its magnitude. Okay, what's the position vector then? The position vector is always you take the final values and subtract the initial values. So you take those coordinates at the end point of this vector and subtract those values at the starting point. So that's going to be 16 minus 0 and minus 18 minus 0 and 0 minus 24. Yeah, let me write it in there. 16 minus 0 is 16 pi, minus 18, so it's minus 18j, and 0 minus that is minus 24k. Divided by the magnitude, so that is 16 squared, plus 18 squared, plus 24 squared. Note you don't put a minus over here and a minus over there, because it's actually minus 18 squared. Actually it should be minus 18 squared. But we leave out the minus because it's going to turn to a plus anyway. But don't put in minuses here. It's minus 18 squared and minus 24 squared. So you get that. And here again, that square root there works out on 34, that value there. So this is just then 16i minus 18j minus 24k. And okay, then you can simplify it from there. So I'll first check what is that square root before, and see if it's, especially if it's an integer, then I can simplify this and then work that out. Yeah. And okay, then you're going to get 600 divided by 34 times 16. That's going to give you the I component, and then 600 times 8 minus 18, etc. And you get those different components. And once again, the magnitude of the force, that one squared plus that one squared plus that one squared, should give you 600. Because that was my force when I started. Okay, these position vectors and unit vectors are quite important, especially what do you subtract from what? And as always, you have the final value, you have the initial value. You take the final value minus the initial value to get the difference. It's the same as on your car. If you have a trip meter, you put it, let's say it's standing at 1,000 and you travel and you get to your final destination and it's at 2,500. Then you're going to say 2,500 minus 1,000. You're not going to say 1,000 minus 2,500. You take the final value minus the initial value. That's a simple way of looking at it. Okay. Let's say something about dot products. Okay, I think you only started yesterday with dot products. Yeah. So, let's just quickly look at the following. There are two problems in your tutorial on dot products. The last two, I'm just going to look at finding the angle between two forces. I think the last one is finding the angle between two forces. Actually, I think you should swap the last two around. First do the last one, and then you can do the second last one. Second last one could take some time. So swap the last two problems around. Okay. The dot product. That's the definition of the dot product. And this is something you're going to use in future chapters in your book. Dot product, and later in a week or two, you're getting to the scalar product. Now the dot product, no, this is the scalar product. Later you're getting to the cross product. Okay, this is the definition of the dot product. Any two vectors, A dot B, is the magnitude of A, the magnitude of B, and the cosine of the angle between the two. The answer here is a scalar. No I, J, and K's here. So that's why they call it a scalar product. Scalar product. Dot product of scalar product. So if I have two forces, F1 and F2, I'll take the magnitude of the one force, magnitude of the other, and the cos of the angle between the two. So that's your definition. So, okay, let's say I want to find the angle between two vectors. What do I need? I need the magnitude of the one force and the magnitude of the other force, and I need the dot product. I need to know what is the dot product. But there's another way of working it out instead of this one here. So let's say you have those two forces there, F1 and F2. And, okay, the magnitude is quite easy. 1 squared plus 2 squared plus 2 squared, square root of 9, and the other one 3 and 4, so the magnitude is 5. So now I have these two. I have the magnitude of that one and that one. There it is. Now I've got to get the dot product between the two. So I write down I minus 2j plus 2k, that one there, and I've got to dot it with 3j plus 4k. Now the way it works is you multiply the I component with the I component, the j component with a j, and the k with a k. Now here you have an I component, but there's no I component. So that's 0. Then you have a minus 6 and a plus 8. Minus 6 and a plus 8, that is 2. So you take the I with the I. If there's no I on either side, then of course it's just 0. And then the j with a j, 2 times 3 is 6, with a minus is minus 6. And then k with a k is 8. So it's 8 minus 6 and a 0, that will give you 2. So there's my dot product. And that is the left-hand side of this equation. This takes a bit of practice. It's maybe for a lot of people a strange concept. But it's quite a handy concept to have later. But anyway, so this is your equation for any two vectors, A and B. They can be two forces, or they can be two unit vectors. In fact, the one can be a force and the other one can be a unit vector. You can have something like this. Let's say you have a force, F1, and here you have a position vector, AB. And you want to find the angle between those two. Then you can also use the dot product, F1 dot, that position vector, AB. Let's take another example. So, okay, let's say I have a force here, a force F, and here I have a unit vector, and I want to know what that angle is. And I say F dot U equals the magnitude of the first one times the magnitude of the second one times the cos of the angle between the two. That's your definition of a dot product. The magnitude of the first, the magnitude of the 7, cos of the angle between the two. And of course, the magnitude of that one is 1. So you need the magnitude of the one force, cos theta, F dot U. And the same if you were to have a position vector and a force vector there, and you want to find this angle, then you can say R dot F equals the magnitude of R times the magnitude of F cos of alpha. And let's go through the dot product itself again. Let's say you have a vector A equals 2i plus 3j minus 5k, and you have a vector B equals I plus j plus k. What is A dot B? A dot B, well, let's write it out. That is my A, and dot with B, I plus j plus k. So the I with the I is 2. The j with the j is 3. And the k with the k is minus 5. Oh, in this case it's 0. So that is your dot product for those two. What does it mean when a dot product is 0? You know that? How? Yeah. Perpendicular, yeah. The vectors are perpendicular. If this left-hand side is 0, if your dot product is 0, then it means cos theta is 0, which means theta is perpendicular, is 90 degrees. So A and B is perpendicular. So, okay, that's the important thing there. Let's see if there's something else. Yeah. So that's the important thing there. The other thing you also did, or the other application of the dot product is when you want to find a component of a force in a certain direction. If you want to know what is this. The last problem, no, the second last problem in today's tutorial. They say find the component of a force or the projection of a force in a certain direction. Now, of course, this is F1 cos theta. You can see it from the triangle there. So that's one way of doing it if you know the angle theta. If you know the angle theta, you can just say that magnitude cos theta, and that is this projection. If you don't know the angle theta, then there's an alternative method of doing it, and that is to say, take that force and dot it with a unit vector along this line. F dot the unit vector along that line. So you need to find the position vector there between any 2 points again. Note your position vector can be between any, if you have a vector in space, you can take any 2 points along that line to get the position vector. And the unit vector will then be that position vector divided by its magnitude. So, the second last problem in today's tutorial, they ask you the component of a force in a certain direction. And then you do it this way. I'm not going to say more about that. The last thing I just want to say is, if I go back, I can go back to this one here. Okay, there's my definition of a dot product between two forces. That means that cos theta equals F1 dot F2 divided by the magnitude of F1 times the magnitude of F2. Now you'll notice in your book, they often write this in a different way. This F1 divided by its magnitude, that one there. What is any vector divided by its magnitude? Unit vector. So this divided by that is the unit vector in the direction of F1. And the same applies for that. That is the unit vector in the direction F2. Because you have this equation that a force F1 is the magnitude of the force times the unit vector in the direction of the force. That unit vector A, B, or BC, but it's in the same direction as the force. And the force F2 is its magnitude times the unit vector in the direction of the force. So the unit vector itself is then the force as a vector divided by its magnitude. That's that one there. And this unit vector is that force divided by its magnitude. So in your book, they often give it like this, and you'll probably see it in the memo of the tutorials. They like to use this notation, but it means exactly the same as that. Okay, any questions? Okay, then I'm done.